Hello, can you hear me? Okay, good. Thank you. Yeah.
And this is my
Logo.
logo too.
Sure, yeah. Is that okay for online people? They can see me. Oh, I see. Okay.
We trace you.
Oh, okay, good.
Okay.
Because I don't want to miss the point. Yeah,
Yeah. Okay.
that'd be great. Yeah.
Okay. You can test a little bit for the yeah because we project the classroom.
The Hong Kong Polytechnic University, PolyU, leverages its world-class academic and research excellence to develop innovative solutions for a more sustainable tomorrow. In July 2022, the PolyU Academy for Interdisciplinary Research PAIR was established as the university's central research platform, dedicated to providing world-leading interdisciplinary solutions to address significant societal challenges. PAIR is composed of multiple constituent research institutes and research centers. Each research unit focuses on a particular research area and is joined by researchers from various PolyU faculties, schools, and departments. PAIR research areas include advanced technologies and manufacturing, good health and well-being, and smart and sustainable cities. PAIR researchers develop new materials, systems, technologies, and techniques that support industrial modernization, upgrading, and transformation, look into the factors and mechanisms influencing human health and wellness, and develop evidence-based solutions, and generate smart technology-based solutions for making urban operations and services more efficient, connected, and eco-friendly. We particularly value impactful collaborative activities in research and scholarship. PAIR researchers pursue research collaboration at different levels. In addition to interdisciplinary collaborations within and between research units, PAIR and its units establish partnerships with industries, governmental bodies, universities, and other external stakeholders. With internal and external collaborations, we have successfully translated PAIR-led innovations into commercializable solutions and practical applications, and established joint laboratories and research entities with external organizations, driving scientific breakthroughs, innovation, and technology development, and socioeconomic prosperity. PAIR's research excellence and research impact have been widely recognized at local, regional, and international levels. Our research outcomes have been published in leading journals, including Nature and Science. Innovations led by PAIR researchers have won prizes at various competitions and events, including the International Exhibition of Inventions Geneva. Many PAIR researchers have been named among the world's top 2% most cited scientists in their own areas of specialty. Individual researchers have been selected to the National Academies of Science or Engineering and as fellows of professional associations, and have been bestowed with local, national, and international awards and honors. Harnessing the strengths of PolyU's research and world-class scholars, PAIR will continue our unwavering efforts in research and scholarship, knowledge transfer, and collaboration to develop impactful solutions that benefit Hong Kong, the nation, and the world.
Good afternoon, ladies and gentlemen, colleagues. My name is Qing Cheng. I am the director of the PolyU Academy for Interdisciplinary Research. It's my great pleasure to welcome all of you to this seminar. And today I'm happy to introduce our distinguished speaker, Professor John ZHAI from the University of Colorado at Boulder. He is actually from the Department of Civil, Environmental, and Architectural Engineering. So Professor ZHAI received 2 PhD degrees, one from Tsinghua University, another from MIT, and one in the fluid mechanics, another in building technology. So it's a pretty rare case. And since he graduated from MIT, he has been working at the Colorado University and focused on sustainable buildings, integrated systems, and the indoor and outdoor environmental quality, with a mission to decarbonize the built environment while ensuring healthy indoor environment. He also served as the site directors of the U.S. National Science Foundation Building Energy Smart Technology Center, or the BEST Center, which bring together industry and academia together to develop smart, energy-efficient building technologies. So Professor ZHAI's work bridges the micro-level energy efficiency with the micro-level environmental physics. He has led pioneering work across a wide range of technologies, from building integrated PV, personalized ventilation and air conditioning systems to natural ventilation and thermal storage. So it's a pretty long introduction. I just wanted to keep a little bit short here. He actually is a Fulbright scholar. That's a very important title for a U.S. scientist, and also an international leader fellows of the Royal Society of New Zealand. And he has advised organizations such as World Bank, Carrier, and Marriott in many major projects worldwide. So without further ado, ladies and gentlemen, please join me in welcoming Professor John ZHAI.
Thank you. Good afternoon, everybody. Thank you, Professor Chen, Professor New, and the peer invitation. It is my greatest honor and a pleasure to be here. This is the first time I actually present and PolyU, so that's my experience, special experience, and to share with the people here and online. So today I will introduce a little bit my personal perspective in the building environment, and which are the two major areas of my research in the last 25 years. So a lot of stuff to summarize my own taken. So you can take whatever you feel you think is right. I will start with the U.S. Department of Energy, BTO, that's a Building Technologies Office, and what their vision for next generation building. So I just want to highlight a few things. One is that's called, the total title is called GEB. It's Great Interactive Efficient Buildings. So you're not talking buildings, it's integrated. And there's some keywords. So it's beyond a building's walls and into the grade of to maximize the energy. Efficient, that's what we talk about, and also buildings and the grade simultaneously. So now the DOE not just talk about one building, they really talk about a set of a building, a group of buildings, and integrate with the energy supply systems. And also there are 4 keywords. You may take a look at energy efficiency. That's all we talk about. And then they talk about connected. Connect the human, connect systems and components to the buildings. And the third one, flexible. So we talk about supply, demand, how to match that. That's flexibility. And the last one is smart. Everybody talk about smart city, smart building. Let's talk about sensor, talk about control. And then we talk about the center. Professor Chen just introduced. I'm the site director for the center. This is built by U.S. National Science Foundation. It's called Building Energy Smart Technologies Center. This is the only center focused on building technologies in U.S. The other centers are transportation, all the stuff, right? This is the only center focused on the building technologies. Again, I don't want to talk about details, but showing here, you see the scale. Again, we're talking not just talk about individual buildings. We talk about expand the communities, and then we expand to the cities. Though that's again the trend. On the demand supply side, you will see we're not just as traditionally talk about demand side, we also have to consider the supply side. And the most important part is the management, how to match the disparity between the supply and the demand. And then this is the slides I showed before other occasions. I think is described in building environment, different scales, both spatial and temporary scales. As we can see, we start with a person. During the pandemic, we talk about aerosol, the particles, those are nanometer, much smaller size. And we talk about human breathing, comfort, and we talk about space, the room conditions. And then we get into the whole buildings. Eventually, we get into the city block and to the global heat island, all the impacts. Energy side, the buildings, energy side, again, we start with the very fundamental building materials. Now people talk about nanomaterials, micro materials, for storage, for installations. Those are down over here. And then we talked about the elements, the window, the door, the wall, the brick. There's a big gap, we'll talk about later, between the materials to the elements. You will see 90% nature science research, they focus on the building materials. However, from 1 inch or 0.1 inch to 1 foot or 1 meter, it's a huge scale up challenge, and we'll talk about that later. And then for the individual buildings, we really talk about the entire building set. and connect with the supply system, where the energy storage play a significant role to manage the balance. This is the slides I draw when I fly to Hong Kong. I was thinking about what's the scale difference in both, like the size difference, right? We talk about airborne constituents. I didn't use pollution or microbeam because airborne stuff could be good. A lot of people talk about air particle, PM 2.5, you talk about CO2, those are bad things. But actually, a bunch of people now study the good thing. How to make people happy, how to make people in good sleep. So why not just talk about general, what's the airborne system? They'll talk about nanometer, micrometer, and the time can be very millisecond reaction to the human. And then we talk about materials, it could be nanomaterials to the concrete break. And the same thing for the human body, and then to the individual buildings, community, region. So you will see the time scales over here. That's a human reaction to any microbeam, to any like heat, humidity is millisecond. You will feel the reaction when you touch some hot stuff. And eventually you talk about 100 years. That's typical people talk about life cycle impacts, right? So from here, you will see the time scale. We talk about 10 to -3 to 10 to 9, the 10 to 12 difference. And the length, it's even much bigger. We talk about 10 to 16. So that is something we never thought about before. We always talk about the building human, but now we need it down to the airborne small particles, very critical for air quality study, and then to the city large scale global impacts. Here in this talk, my personal division as like I'm talking about there are both environment and energy side. For the micro, I define as the nanomaterials. So we talk about airborne constitutes the environment impact, and then we'll talk about the meso side. We'll look at the human comfort and talk about building individual buildings, and then we move on to the city community impacts. Eventually, I will talk about regional global challenges. So that's all structure for today's talk. All right, let's look at the fundamental micro, the small size, the airborne constitutes. So what are the problems we're facing, we haven't figured out? Here, I'll share some of the research we done in our lab. Again, those are just a very small fraction of examples, and you can imagine there are a lot of stuff we don't know yet. And we look at airborne constitute sources. There are different sources. Could be gas phase, could be particle, droplet. They are totally different. Could be most people look at spheric one, but really the particle, we don't know the shape. It could be irregular shape. How this is going to different from the spheric? Nobody knows. And then we'll look at how the sediment. For example, you have a carpet over here, but you have a smooth wall, right? You have acoustics wall over there. How the particle can attach to different walls, that's sediment. We don't know that. And certainly a lot of chemical reaction, polymetallicization, a lot of stuff beyond our knowledge, actually. The building guy don't know how this got reacted. So this is just one example we did in pandemic. This is rated as a highly cited paper over 1,000 in 2 years. Everybody want to talk about why the government says you need to keep 2 meters away, right? During the pandemic, 6 feet in US. Why is that? Nobody actually talk about it. What's the ration behind it? Why not the 1 meter, 1.5 meter, why you talk about 2 meters? So we really look at the human talking, how many particles to generate when the regular talk. I'm not talking about special coughing. Those are different, right? When you cough and sneeze, it depends on person. They're all dependent. But talking is pretty much similar. When you have talking, how many particles generated? So we look at those particles numbers, and you find a majority of particles within this 50 to 100 micron. They're basically visible. You see somebody spit out, right? That's all the visible particles. Majority of that in that range. And you'll find actually 80% of the particles will drop to the floor in 2 meters. However, you still have like 10 to 20%. They're going to fly beyond 2 meters. That means stay 2 meters away doesn't guarantee there's no infection. So that's the actually foundation for later people talk about airborne impact. If you fall away from each other, you still may be affected. Yes, that's exactly 10 to 20%. So I always want to emphasize where people in this area, you don't want to emphasize, oh, the airborne's traumatic and circulate the virus. No, 80% still the short distance one. The really airborne part is about 10 to 20%. And also, when you look at the particle less than 5 micron, actually, they can spread really long. If there's no block, no walls, you can go to 2,500 meters, which that's airborne particle transmission, the foundation. And based on that, we developed modify the widely used Walsh-Rayleigh equation that simulate person infection risk. So what we did is we just added this probability for the social distance. And also another one adding into is called air distribution effectiveness, because depending on your supply systems, this is also going to affect your infection risk. So we add this to, and then we compare to a few noted incident during the pandemic. They have a very good match. And this paper, that's people like to see compare with the real situation. And this is 2020, the pandemic just started. We collect data and compare with the model. And then we can use that model to project, what if I have a double space, right? 2 meters away each, depending on how long you will be in this space and what's the infection risk. So general recommendation we got is basically if you rush into a shopping grocery store for 30 minutes, you are okay. You pretty much won't be. But as a cashier who worked there 8 hours a day, unfortunately, even with low concentration, likely this guy will be infected because they stay much longer time. All right, another challenge for the particle is we really look at the particle matter in solid, liquid. How do they collide each other? You'll find a lot of study right now, they assuming there's a number of particle come in with this size, and then eventually get out of space with the same size. You think about it, the real case, the droplet come in. The small droplet can become a big droplet when they hit each other, right? And the big one can break it down to small. Reality speaking, they won't be keeping the same sizes during the process. But none of people done that. Why is that? It's complicated. How do we define that? We don't even know where they go, right? That's the challenges. So we wanted to really look at how when they hit each other, for droplet, it's a little bit easier. Droplet always attach. What about solid? They can attach, they can split. That's a complication. And another complication, this is actually Professor Chris Chow spent 20 years around this one, vibration. What if I have a speaker, give a little bit disturbance? Can we help this collision make a small particle bigger, eventually drop on the floor? So in that case, you don't need air cleaning devices. That's smart, right? So what do we do? How do we use the speak to vibrate, motivate these particles, make them either break or collide each other? There's some interesting ideas. And the last one, for those of you who did the particle study, you know the common recommendation is 5,000 particles, because you want to track every single particle. It takes time, take effort. 5,000, it's a middle. It gives you statistically meaningful results. However, it doesn't take too much effort to track every single particle, right? But as I said it before, when I talk every minute, I spread out 3,000 particles. In this space, all these particles, millions. Why 5,000? It should be 5 million, right? So how do you track 5 million particles in the space? Nobody talk about it. You cannot model 5 million particles in the space. You can track it. No way. With the supercomputer, you have no way to model it. How do we do that? So that's another challenge we have to look at. So this is the study we did in our lab with a PhD student. We did both experimental study and also with the LES model. I don't want to talk about details. Again, it just highlights some outcomes for discussion. And you can see this is a regular case inlet. If we don't do any collision, you basically pretty much the same as inlet. When you add the collision model, at wall collision model, at vibration, you will really see about 15% reduction, the total particle numbers, and the size change. So then we did a more test on that. We say, what variable is going to affect my results, right? So that question, you can think about it. So number one, we look at change intensity, big vibration, how this is going to change and you look at frequency. Actually, low frequency is better, right? And you look at over here, the flow rate. We find a slow flow rate is better. And eventually, we look at the particle concentration. Dirty environment, the vibration place much better than the low concentration. That all makes sense. But due to the limit of at the time, we could not conclude which was best, because really the speaker can have wide range of the speak possibility. We haven't tested that. Eventually somebody should do that. What is the best vibration speak we should develop? So eventually we can change the whole filtration technologies. And then to the material side, we look at the new materials. A lot of the keywords we look at biomaterials, new renewable energy, phase-changing material, like Professor Neil this morning at the conference talked about phase-changing materials and moisture issue, the Hong Kong, and also talk about smart materials, low carbon materials, life cycle, scale up. We talk about from a couple inch to a couple meter. That's a huge challenge. I will show you example, a field example we did. And then certainly we also look at age material. Very few people talk about age materials. For example, the insulation of this wall, been there for 40 years. What is the property right now? You'll say, what are you value going to use? You used original manufacturer value, right? That's my conductivity value. After 40 years, the value is totally different. When you do building retrofit, you cannot use that one. If you use that one, you got wrong optimization results, because it assumes this as new, but after 40 years, it may already have moisture inside. This insulation is not insulation anymore. So that's all degradation. That's all one of my research area right now in our group. So this is some ideas we had before with the brazing wall. So we need a fresh air anyway. Why you want a mechanical system so complicated supply to the wall, to the space? Can we just supply to the wall, have all the holes, and you get heat recovery, right? So this is called dynamic envelope. It's right now very popular in US. People are developing all kinds of dynamic envelope. Somebody look at it by mimicry from animals, the leaves, plants, understand what material can do. And we did an experiment trying to understand how the dynamic wall efficiency change with the temperature difference, indoor-outer temperature difference, and with the airflow rate. It does matter with all these variables, with all the measurement. And then based on that, we wrote a big giant proposal, the single PI proposal. This is the largest one US National Science Foundation supported, $2.5 million just for myself to develop this crazy idea. It's called living wall. Can we develop something like a human skin? Why the wall won't like a skin? What we have for skin, right? Skin is sweating, right? We have a muscle, we have fat, well, all the blood flow, right? And you remember when the outside hot or cold, your organs always keep at 37 degrees Celsius. How do we adjust to that? Certainly we put a clothes on it, take clothes off. That's insulation. But besides that, what else? Our human body can adapt to the environment. This is very important. So we want to mimic with that environment. So we worked with a bunch of people in the material science with the, I don't want to talk details, trying to develop materials like that. So long story short, after 5 years study with $2.5 million US, it worked somehow. We developed a nail size, this size of materials. It worked like we expected. However, we never ever scale up to a break size because of cost. So we can publish on Nature Science, but unfortunately nobody would use it. I have no idea when. Somebody may pick up these ideas and eventually develop a commercial. We finish our task because National Science Foundation interested in the concept, the prototype. They never care about it. Really, people can use it. But what I'm saying, that's the challenges, the difference between basic science versus application study. And the architects even get the imaginary wall based on that concept. They say, you should have the wall like this. And we did it. But unfortunately, nobody can produce it. With today's 3D printing, maybe there's a way we can do it, but we haven't tried it. And our engineering student developed a tool. This is a generic tool. People can analyze any specs, any wall, real or not real. You can put in there, you can try what's the performance. For example, you can put glazing on it. You can have a cavity somewhere. You can put phase change material, any layers. It doesn't consider the structure. Any layer you can think about it. We can get the performance of this wall. And we give you the temperature at surface, and we got the air velocity and air temperatures in the cavity. We can do this. And the Singapore airport development, they used our tool to simulate the inside, because in Singapore new airport, they have the waterfall stuff. There's condensation issues. So we use the software to simulate it. And further, we're linked to a transit whole house model, because that one just for one wall. Eventually, we want to estimate the whole buildings. That's why we integrate with the buildings, see how the buildings can perform with this wall. And for the aged material, this is a very hot topic. Department of Energy, US, care about it. 75 buildings in US, commercial buildings, built 1980s, which means they already have like 40 years age. So all this building envelopes, at the end, I'm going to talk about mechanical systems. Mechanical system for sure, 20, 30 years and. Building materials, 40 and. How do we replace that? How do we identify which window, which wall is not right? We need to replace it. So this one to talk about window. We never thought about windows issue. When you look at a window in this building, if it's not broken, nobody gonna care. It's a window, it's over there, right? You got the light in, you can open it, it's all good. Actually, the windows age, window glazing, it's about 10 years. After 10 years, the properties, the low E, the argon, all the stuff all gone. So they're never gonna share the same properties as original, but nobody talk about it. So we look at the mechanism of the failure mechanism of the windows, because window is the weakness of the building envelope. You think about it. Typical wall, U value, R value, with US we call R value, is about R13. R30. That's the R, the resistance. Higher resistance is better, R30. The best window on the market, the best one, R7. If I have one layer, R1. 2 layer, R2. It's very simple. 3 layer, R3. But the cheap installation, R30. So window, whenever you have window, that's your thermal bridge. You put a good insulation, doesn't help because majority heat gonna go through the windows. So window will be the key. That's US DOE definition. Will be the key for the next generation retrofit. So that's why we look at it. So you look at all the low E argon. If the argon is gone, eventually you got low E air. If the low E is gone, you basically got a clear argon, all clear air. So we can estimate the energy change. So this is just showing if, let's say low E argon to clear argon means low E peel off. You don't see low E anymore. The cooling impact, 10%. The heating impact, 20% for heating, cooling. What if I have the argon is gone? You will see about 9%, 22%. This is the first time, let me go back. First time we find argon doesn't really help with the insulation. We never thought about it. We also, hey, you just have a vacuum, you're putting argon in, that's argon is something that transfer heat. No. It turns out people putting argon is to stabilize low E. So that's a purpose for argon. It's not for insulation. All right. So now we move on to, because of time, I'll move on to the occupant. The occupant level, we talk about adaptive heat, holistic heat, thermal comfort. Many people, especially in Hong Kong and Singapore, Japan, China, South Korea, done a lot of thermal comfort studies. Not many in US because there's so many regulations preventing doing all the real person tests. So we don't have many research in US, unfortunately. But a lot of studies, and people talk about non-uniformity and talk about personalized, localized. Professor Jianlei Niu is an expert on the localized control. So this is the study we did. Actually, we talk about when people sleep. When you, in the hot day, you sleep, you have a fan on, you feel it's cold, not good. However, when you put on your back, you're still sweating. You see, the top part is cold, the bottom part is hot. So obviously, you have two index, right, for your comfort. The people in the Denmark, they divided people into hundreds spots to analyze human comfort. In our study, only divided 2 pieces based on basic heat transfer. Number one, the top part, convection. The bottom part, conduction, right? That's contact of the back. So with the simple 2-node model, we'd be able to simulate the human comfort during the sleep. And based on that, we can adjust either the fan, air condition, or the beddings set up to make people happy. So this is a very simple example showing really something we haven't thought about it with not just one person, but 2 nodes during this special sleeping condition. And this is another study. You look at all the comfort index indoor. Nobody talk about solar because we assume there's no solar, no window like in this one, no solar. But in the real case, your house, you always got a window. You have a solar. When you have solar on the body, your comfort index will be different. Should you turn on off your AC, also depending on this solar. But all the standard, inside standard, there's no solar impact. So we're trying to develop a model, include this is the first model, consider solar impact. And now it's not into the standard yet, but it's already highly cited by the expert in this areas. Okay, this really make the comfort model complete. And then personalized control, right? Professor Neil's expert in this, he did a lot of, we cited his work. Professor Fanga, Denmark, in 1990s, he presented, say that for next 20 years, next generation HVAC system should be localized, personalized. So now he passed away, 20 years also passed. How many personalized systems you see in practice? Not many. What's the problem? What's the problem? The idea is so great. Everybody get your own jet, right? You can adjust based on your, people use that for automobile. You go to your car, you have all the jet, right? Why not use for the indoor environment? People argue, oh yes, because engineering practice is so complicated. Everybody have your intake, right? Exhaust. No, not really. Fundamentally, this is Professor Neil's work back to 2006. So this is 20 years ago. They already have the fundamental study, but I don't know, this was not, I didn't see anything in any classroom yet. And this is a company, Sweden, they even produced the prototype of the systems, but you never see on the market. What is the problem? So nice, so good, personalized, they have benefit, air conditioning, the thermal comfort, benefit, air quality, great. So we did a thorough search, compare all the lessons, experience people accumulated. So in this paper, 2019, we list those are stuff all the study agree on. That's all good. However, there's something, somebody say not good, somebody say good. There's conflicting informations. So really what affected the people's feeling, that's something we don't even understand clearly. And besides that, people concerned about energy consumption. Everybody get your own little intake. What about energy consumption? So we have to consider all the balance with indoor air quality, comfort, and energy use. A lot of people, like a Boeing company, they want to have the jet, all the stuff, right? Nozzle. Does that for your air quality issue or for cooling issue? Professor Chen's expert on the aircraft design. When we talk about that during the pandemic, people argue, hey, should I turn on this guy, right? Or turn it off? The final recommendations, don't do anything. If it's on, just keep on, right? Because if it's on, you're the source. You're going to spread out the virus everywhere. Okay, but if you're not the source, your neighbor is the source, this guy turned on, all the virus is going to get to you. So what are you going to do? Right? But eventually, originally, the idea for this guy is for not for air quality, is for fast cooling. When you get on the plane, you want to cool, the sanctuary is not cool enough, this will provide enough cooling, quick cooling. So there's different purposes. Eventually, for our working environment, we have to balance the comfort, air quality, and energy use. So I don't want to talk too much of the study we've done with the air quality and how balanced with the thermal comfort, energy use, and then make a compromise of the systems. And this is actually Professor Chen's work with all the new inverse design optimization. This is the brand new areas we start from human and backward to design all the innovative systems, right? This is never done without the current advanced computing model, algorithms, etc. All right, so the building side, we talk about smart control, we talk about sensoring, a lot of sensor technologies, retrofit, degrade ready, renewable integration, energy storage. So this one's a very interesting story. We worked with Lawrence Berkeley National Lab. Luckily, we got over 2,000 buildings data. They have different levels of sensors. And we want to see, when we install more sensors, can we get more benefit of energy saving? Because when you talk to an expert or sales, they say, hey, Dr. ZHAI, you need to install more sensors. You not just monitor the whole building utility. You should have lighting, HVAC, elevator, right? Each have your own monitor. And if say you should have a monitor for your boiler, for your heat pump, for your AC. And somebody say, no, you need more sensors. Every single window, every single light, they should have a sensor. Right? For the sensor company, it doesn't make sense, right? They want to sell more sensors. But the question is, what's the benefit? When you add more sensors, can this really give you a benefit? So that's the study we've done. So I showed it here quickly. I don't want time to look at it. And we even got this cost. What's the hardware cost when you add all the sensors? And what is the cost saving? So generally, the sensor can be divided into 4 levels. One, whole house. Like in your house, you got a utility pay, that's it, including electricity, whatever, the gas. Or some countries, I don't know, Hong Kong, US, we have this electricity, this the water, this the gas, right? And you can do that. That's all categories. And you can go systems. This is my heating, cooling, elevator, lighting. That's a system level. Further to element, you can lighting. The general conclusion is overall, whole building sensor is needed. It will help you. Any system go beyond doesn't help you at all, unless you have a BAS systems, building automated control. What that means, something's wrong, you have automatic control, you will adjust that. Oh, the lighting sensor, somebody not in this room, lighting is still on, automatic turn it off. You got a benefit. If you count on person, let's say nobody here, the last person living in this room should turn off the lights. Human is not reliable. If you rely on that, you don't have any benefit at all. So basically, our conclusion is you should do high level, it's good enough. Without a BAS, don't go deeper. It doesn't give you any payback. And this is the current study. We wanted to detect the failure. We talk about the failures. In practice, how do we detect that? So those are the horrors, or the clad on the wall. Traditional method, you had every single person knock on the clad. You to the hollow sound, you identify it. You think about it. I was just at Opera House. Opera House, they do this. There's in Sydney, right? Opera House. They said they do this, take a couple weeks to knock every single clad. They cannot do this every year. They have to do every couple years because costs are huge. So now we think about, can we use a drone just to fly through in the thermal image and then identify which one is loose when you replace that? Because the loose one are huge, dangerous. You think about all the fall, right, to the head, all the stuff. And further than that, what about glass? Glass is so difficult because any shadow and the sunlight reflection is going to affect thermal image results. We haven't found a solution yet, but that's a challenge we're doing right now. Can we do at night? At least you don't have solar, you don't have shadow. Can we do night? There's something else going on we haven't figured out. The traditional thermal image may not be able to provide answer. And then we talk about window retrofit. This is an ongoing project supported by US DOE. We said, can we add addition, retrofit existing window, not interrupt the current building operation? Because people say, my window's okay, my glass is okay, why should I replace it? I said, no, you don't have to do anything. I will have another layer of window, and this can help you the thermal comfort energy issue. We did that. And this is called secondary windows. We work on it. This is a very cheap one, very easy. Everybody here can do it. And you can do it for your house. But the problem is the condensation. When you add the layer, you basically have the cavity inside. This cavity will cause condensation. And the temperature inside will be below dew point temperature. That's a huge problem. That's our projection for the whole United States. You will see the areas with all the problem, and we have a 24/7 different months as you see the problem. Industry denying this findings. Says, no, we never find that. Because this stuff happened at early morning, you see? And people wake up, it's gone. But doesn't mean there's no damage to the window. Water is still there. right? So that's a problem. So when we're talking to the industry, they're trying to revise that technologies. And this is another very interesting stuff we just finished this research. This is called building integrated PV. Can we replace all the windows with a PV window? You guys know that, right? Transparent windows. Can this provide enough electricity for our building? Right? We use a very simple 3-story commercial building in the US in Denver. Unfortunately, look at this one. For 98%, that's a maximum glass, all glass buildings basically. What you got is only 8% of the HVAC energy can be provided by this window PV. So eventually, I will give another talk at the conference. Eventually, don't count on the building integrate PV to solve your energy demand. There's no way. And then you ask, then what? So we have to purchase from green power plants. So never ever for buildings higher than stories, there's no hope. For US, 1 story, 2 story, yes, we're good, we can do it. For any high-rise buildings, unfortunately, no, there's no hope. We can count on the building integrated facade by optimizing geometry, provide enough electricity, no hope. And only if we change the solar technologies, solar materials, which, by the way, won't be possible in the next 20 years, according to the US National Renewable Energy Lab chief engineer. He said in his 70s, he said by his lifetime, he won't be able to see any breakthrough of the new materials. And this is what we did, right? So what if we go from this very cube rectangular geometry with the architect students? I do no limitation on the structure. Statics, don't worry about the ugly, whatever, right? Do the best, the maximum solar exposure. That's what we did eventually. And we can match with all the best PV on different shadow shading devices. So this is a framework, I will skip it. And it also, this is the talk about shape of grammar. So it's not random change the shape. It follow architecture rules. Okay, architects still follow all the shape of grammar. And eventually you will see over here, it's very small. You see, that's the best one. We got a PV generation is 1.94, which is 20 kilowatts per square meter per year. What does that mean? 20 kilowatts per square floor area per year. I don't know Hong Kong, US commercial building, 200 kilowatts per square meter per year. You only talk about 10%, right? 20. The best energy efficient building, German passive house, 42 kilowatt hour per square meter. You not even catch half of that, right? For best. So this again confirm, yes, we won't be able to do that in the. All right. So this one's talk about some solar storage. Right now, working on the chemical reaction solar storage technology is called modular heat batteries. We can store the heat during the daytime and basically dry air. They separate the wet salt to a dry salt and the moisture. When you use it, you just put humid air through the battery, you got the heat back. So this can guarantee your seasonal heat storage. And we tried it with the building application. I'm gonna skip that. And now let's look at the macro district cities levels. So basically talk about heat island, microenvironment, urban pollution, urban energy stock. I'll give some examples. This is the one example we did with this we call cruise vehicle, make 3 stop, and we can, based on the projection, the weather data, we'll be able to predict the sources in the city, and we can have a drone to verify that. This technology being used for multiple industrial parks in China to check the leak for this industrial leak at night, usually happen at middle night. So we'd be able to track where this guy just released the pollution for 20 minutes at middle night. We should be able to find that. And this is microenvironment, and this Professor New actually had a big giant project work on the microenvironment. We wanted to look at how important microenvironment to us. Everybody talk about the campus temperature is different from the airport. Yeah, we know that. So what? Why this is important? So that's all we wanted to look at. So I'll skip the details, but give you the answers. We find our university weather station is about 2 degrees, 1.7 degrees C higher than the local airport. Airport is only about 4 kilometers. away from the campus, not far away. But it's about 1.7, which is similar to others' research. However, we do find a strong correlation between dry bulb temperature and dew point temperature. So temperature is not a big issue. The big issue is wind speed and solar radiation. Because the airport, that's a plant, there's no obstruction to the wind, to the solar. Any building on site, you will blocked by the neighboring buildings, right? So that makes sense. Then we did the energy calculation. If you really just care about total energy consumption, care about carbon emission, difference of 2%. Not big deal. 2% consider all the uncertainty is nothing. However, if somebody interested about systems, the heating cooling system could be huge, and the peak load can also be huge difference. So if those guys in the HVAC industry, heating, cooling, you have to care about that. If you only talk about heat island, energy issue, right? Nope. Personally, I was thinking that's not a big issue at all. And this, the building stock, we'll look at not just one building. We talk about a bunch of buildings, city buildings. You have a residential building, commercial building. They have different peaks, right? What's the final peak of the city depending on what percentage? How many residential buildings do you have? How many commercial buildings you have? Why this is important, I will tell you next. So we developed a method called stochastic deterministic couple method. So we have to consider uncertainty. When you handle this million houses in these buildings, you don't know a lot about the building schedule, building occupancy, right? You don't know set point, you don't know installation, window conditions. What do you do? Right? You cannot model every single building. So how do we do that? You have to consider uncertainty. That's why we developed a method called stochastic. And deterministic, we still use engineering tool that can provide X to getting to Y, but X is profile and the Y will be the profile too. So this is the methodology used to use the measured energy data to calibrate basically the basic calibration. We know the input profiles. And then we can get the total energy use of the space. Upon that, we can see the strategy. Let's say the university, the president, gave $1 million or $10 million next year. As a professor in this department, can you guys, can you recommend where should I put this $10 million for retrofit? Should I, every single building should get $500,000 to replace what? Window, door, envelope? Or should I just focus on one building? You have to make a recommendation. That's just for campus. You think about the whole city. If the Hong Kong government get 10 trillion, right, next year, as an expert, you have to make a suggestion. So that is what we can do with this model. With that model, I can say, what if I replace the old windows by this percent? What is a benefit I can see? So really for the policy decision making. And this is another, we expand that to the social science. What if I consider the populations, the age, the access to the facilities, medical facility, then we can identify which one is a high risk old neighborhood. So really the social problem is not just engineering data. You talk about how many people's education, the income, accessibility to the facility, etc. All right, so now let's get into the final regional global one. That's a lot of people talk about global warming, extreme conditions, weathers, and the dynamic interactions. So this is a study we done in 2019, global warming. Everybody talk about global warming. I think Professor Chen's group also did a study on the global warming. We just chase after, say, hey, let's look at global warming. We find that there are different groups have total different answers. Some groups said, well, global warming is terrible. It's coming like a Trump's government deny the global warming, right? There's no global warming, everything's fine. And Biden's government said, no, global warming's there, right? So which was right? And then we find over 30 models in the world, they can do global warming study. Some results give you very high projection, and some give you nothing. Very interesting, all from the scientific research. So we group all these 30 models into 4 levels. We call low model, low middle, middle high, high model. They give you total different answers and very interesting stuff. And we use that to predict the building energy use. And this one's special. We also, not just temperature, look at humidity, like Hong Kong. What if for the next 20 years, the humidity increased by 20%? What is the impact? So we can do that too. And eventually, what we did is this is a classic, the climate zones in US. And we can, based on the results, we can show for the next 100 years, this high red one, which means the climate zone can change twice, 2 levels. And the yellow one going to change 1 levels. And the green one never going to change. So we'll give you the indication when you design the buildings, the climate zone will be different. And this is our last one was Professor Dai from Shanghai University of Science and Technology. That's a new one. We just started last year. So you guys know that China is doing all the low altitude economy. So use the drone to deliver the food, right? All this stuff. The question is, there's no regulation on the safety of the flight. All the regulation is based on high elevate, which is 10,000 meters. But typical, this one is less than 600. So 600 is within the building range, right? The boundary layer of buildings. How do we get that? How do we find this one? So the wind tunnel experiments been done to see the dynamics and also do the real flight. Okay, so that is the animation doesn't work. But anyway, this is an ongoing project. We're doing the wind tunnel testing, and also we're doing the real regional test to see the safety. Eventually, think about it. In 20 years, you will see hundreds of thousands of drones fly around the Hong Kong sky. What do you feel? You like it or not? I heard somebody talk noise issue, right? I will worry about it, the crash of this drone gonna hit my head, hit my car, right? What we can do? Nobody talk about it. Everybody's talking about convenience, but nobody talk about safety yet. I think safety is the first step before we can promote any new technology. And that's it. Thank you so much.
Okay, thank you, John, for the excellent presentation. May I ask you to take a seat? And as we are aware, actually, today we have another conference ongoing. We take away John from that conference here because we want to reach a wider range of audience. We have many online attendance as well, and that is the purpose. And under the leadership of Professor Chen, and Temporally will build this interdisciplinary research platform so that many of the keynote speakers, their information can be shared by a large range of audience. And today, I'm not sure we have maybe 10,000 of online attendance. And therefore, we give the opportunity for our audience to have your questions for Professor ZHAI. May I invite questions from the floor? Yes, we're there, please.
Yeah, thank you for the very innovative presentation. So I'm actually also researching in the same area. So I have a few questions. So first is like for energy efficiency of, improving energy efficiency of the buildings, we have several measures, for example, like retrofit or retro commissioning. But it seems like the retrofit rate, at least in Hong Kong or in US, actually not very high. I remember in Hong Kong, it's about only 1% of the buildings. Through the years, we have actually put a lot of efforts to promote it, but it seems like not very progressive. So I'm not very sure if you have any insights of this, like how to improve it and how it will go. Another question is like I'm researching on retro commissioning. It's actually minor measurements. So it was initiated in the US, and also there was a database of that. But I think during the past few years, there was no actually further research in this area in the US. So in Hong Kong right now, we are promoting retro commissioning actually. So I want to know the reason why US stopped to do or like not very put more effort on it? And also I want to know the difference between different regions, because you mentioned about Germany or Europe. So I'm not very sure if there's any similarity and differences between those regions, Europe, Asia, US. Yeah, thank you.
Okay, great. Thank you. I answer the second question first. Retro commissioning is a common practice now in US. It's nothing new. Even 20 years ago when I joined this faculty, people already talk about it. But that time, people only talk about low-hanging fruits. There's mostly talk about commissioning as like a control set point, right? That's a retro commissioning doing so I don't think US also still doing that. And it's not like nobody doing that. It's just when you get into deep into new systems, when you replace advanced technologies, there's a cost benefit analysis. Like I said, the Windows, for example, right? So the Windows still work. It's not broken. Should I replace it? I know the benefit. Traditional single pane. Should I replace with a double pane? And if you do the cost analysis, benefit, and you find it doesn't make sense, because your replace cost is huge because of the both labor and materials, and the benefit maybe only 2 or 3%. So that is a problem. And now people want to add the comfort level. Let's say, no, not just the direct energy cost, but also the people talk about operation cost, but they also talk about human benefit. To argue with that, what I'm saying is like retro commissioning is a common practice. People doing that a lot, but they're still focused on the very low hanging fruits, low technologies, adjust the, make sure this back to original condition, it's a set point, there's shift to whatever, right? That's all they do. Weatherization, there's a leak, let's seal the leak. Those are simple solutions doing that. I think that's something that's going. And back to your question, different countries, yes, huge difference. Europe, Japan, and even US. US is different country because it's the United States. Each state, they have their own saying. Like Colorado, we don't follow California. California have a very strict energy efficient. We are still at the 2004 standard. We can decide. University can override the state regulation. Our university want to go green, so we get into 2020 standards. Although the state says 2004, right? So each lower part can override the upside. That's why if somebody go to Texas, for example, there may not be any regulation. You can do whatever you want. You remember Tesla, Elon Musk has a boxable house. You guys may have heard about it. A box. The box is $10,000 US. You can buy one and you can stack up. A lot of people say, oh, Elon's living in this house. I should buy it. This house we studied only can be sold in Las Vegas because it doesn't have any regulations. There's no structure regulation. There's no fire, no installation. You can do whatever you want. They cannot sell this house in Colorado at all. That's back to your question. So really very significant between New York City to Los Angeles will be totally different, right? So that's for the retro commissioning. But short answer, yes, it's everywhere. And the first question you say it's not the high percentage of Hong Kongs that for the retrofit. The retrofit. Only 1% suitable for retrofit.
Only 1% of the buildings have gone through the retrofit. So it's
okay.
very low
Yeah,
rate.
Let's say that's.
Yeah, only 1% of the existing buildings. But actually we put a lot of effort on it, like policies, regulations, blah, blah, blah. So I just want to know the reason why it's still so low after several years. And another reason is, can we have succeed in retrofit, make buildings more efficient? I mean, just like EV industry or like electric cars or something. Yeah. Because those industries are very successful, actually.
Right. So I always said to my students, 2C only works. One's the cost. The second is code. So either you make sure you're cost efficient. People can buy it. Any recommendation to the industry, to the tenant, to the owner, you have to show them, hey, there's a benefit, right? You do it. Or the government, the code is standard. Government impose a standard. You have to go through this. Otherwise, there's a penalty. That's only two ways. There's no any motivation for private sector to renovate the buildings. Trust me, I did everything with US industry. There's no motivation. The only motivation is standard or cost. So standard says you have to do double pane. Sorry, you have to replace all the single pane with double pane window because otherwise you don't get license. You cannot rent a house, right? That's the code. Or you just showing, hey, when you improve your window, you can rent this house double price. People happy to do that. Just like this morning, MIT professor showed the same example. You know, when you sell this, you show the benefit to the landlord. Hey, there's a benefit, you can rent more, then people will take it. Other than that, the only thing is a failure. Let's say the AC is down. Sorry, this building AC is down. You have to replace it. You have to call the president. Sorry, $5 million, replace the AC. That's the only chance you got a replacement. That's unfortunate. That's the reality. It's any human being, the common sense, right? If your house, you think about it. Why you change my window? My window's okay. It's not broken. There's no reason. I didn't feel any bad. I need a little bit more AC during the summer. That's it. Why bother? When I replace the window, $100K, right? I cannot afford that.
Yeah.
That's the reality. But eventually I was thinking, same Hong Kong, same US, building getting older and older. Something will happen. Like all the windows gonna shaking, right? They're gonna fall, the cat are gonna fall, and that's dangerous. The government will ask the university to recheck all the campus buildings, make sure there's no loose windows, no loose claddings, right? It's gonna happen. But that's not preventive. That's basically responsive, right? Oh yeah, something's gonna happen, I will fix it. Can we do preventive before this happens to do it? That's something as a researcher we should look at it.
Okay.
Thank you.
Great, thank you, John. Now on my screen, I have a list of questions from our online restaurants, and some are actually preloaded questions from restaurants written in written form. So I'll ask question from last first. I'll read the Chinese question in Chinese first. 全球尺度的气候变化与能源转型如何传导并影响微观建筑室内环境？环境的一个是健康，另外就是一个舒适。相应的这个适应性策略是什么 ？And I'll try to do a Chinese translation, the English translation properly.
Okay.
I'll answer the question. Yeah.
Yeah, the question is talk about global models for this climate change or how to affect the individual buildings, energy efficient house. That's a huge challenge, the scale difference. We're not even talking about global, talk about regional. For example, Denver, we're in Denver, Boulder. How do we link to Rocky Mountain area? I'm not even talking about US, Rocky Mountain area, link to it. The connection, the scale difference, talk about 10 to 16, remember, talk about that. The model, each sector will have our own model. Link them together, that's a huge difference. This is more like two departments, two animals. We wanted them to talk to each other in the same language. That's a major difference, major challenges. I don't think anybody did that. That's number one. Number two, when you talk of global impact, you not just talk about air. You talk about vegetation. You talk about forest. You talk about water, rain. That is total different variables from building site. So that's why I make the problem more complicated. We did a study on the local community. We found the greening on the ground. The model for that, if you have a grass, right, have a what we call pocket park. It's a small green. It's not a big central park. It's small green. How this can affect your community? No answer. We tried all the model, never match experiment. So we don't even have a model for that. You think about what if I have another hill, another water body? How did this? That's all the challenge we talk about. We never, I think in the next 10 years, likely still no answer to the global, unfortunately.
Before I relay the question from the online version, we have a question from the floor. Another question from. Yeah, I give the priority to our audience on site. Any more questions? Yeah, here.
And my major is the indoor air quality and aerosol transmissions. And I'm impressed by the idea, the crazy idea about the breathing walls and the living walls. So currently, the 3D printing can also use the biomaterials to make that. So what's can you make some suggestions, or there any available to use the 3D printing for the building envelopes?
Yeah. Good question. Yeah, that's as I said, I think a 3D printing technology is a potential to produce such technology or promote this technology to a larger scale. I believe it can, but again, back to cost. You can print it.
Yeah.
A lot of people talk about use a 3D printer to build the buildings. I think this is a stupid suggestion because 3D printer should make this irregular stuff, like making tools. That's all good because everybody personal or irregular joints for aircraft. That's all cost efficient. But you don't use a 3D printer to print brake. It's because brake is so simple. Why use 3D printer so high tech to build this small brake? That's the same question because eventually this wall will be a brake, right? This is just new material brake. But if you use this $100 brake, nobody gonna buy it. It's just concept. So eventually it's still back to how do we lower the price? So anything we study, I think all my design philosophy, all of my teaching, I keep my students ask the 2 C's. Does the code allow it, require it? And what's the cost? Because every single person, not just the private sector, government will ask the same question. Why you do this? What's the benefit? How soon I can take the money back? Or if I'm not money back, what else? Like a house, comfort, can I argue with that? Oh, no, don't worry about the cost, but the people got more healthy, right? That's fine. That's argument. So we have to talk about one argument, convincing the investor that is something we should do.
Thanks for your answer.
Okay, maybe then I relay this question from audience. I think maybe I add my comment first. I think because I think the message we learned from you is that we should consider both the time scale, but also the spatial scale in whether we are assessing the health risk, comfort, or the energy, I think. Of course, there are short scale and in terms of time scale, there are short-term, long-term effect.
Yes.
But I think this audience gave a very thoughtful question here. I try to relate in my own wording because it's a lengthy question. Considering if we consider the current, say, sustainable design strategies, we are thinking, will there be some cross-scale loopholes that may undermine those, say, the long-term performances of the current strategies? And should the research community reorientate its modeling and design paradigm to anticipate such emergent possibilities? I think it's a very challenging question. I don't quite understand the question, to be honest. Okay. Maybe I can relate to you.
Well, if I understand the question right, I think for the green design, the loop is here. We're still separated person, like a system people, the retro commissioning people, we're all separate. Fundamentally, I think we need to get together. One example is I got involved in the Empire State Building retrofit. That's I'll use that example. The problem with the Empire State Building was the boiler failed. So they need to change the boiler. The boiler changing itself is $500,000. It's on the roof. Okay, this is historical buildings. However, when people are trying to fix that boiler, $500,000, they got a budget. And they find they cannot because the old roof cannot hold the weight of the new boiler. So they have to reinforce the roof first, which is a couple million US dollars to reinforce that roof before you can put the new boiler on it. That's a problem. And they don't have budget for it. What do we do? And this historical buildings, you cannot change the appearance of this building. You cannot change it like another something at another, you cannot do it. So eventually, if you're still doing the HVAC people recommendations, something, let's do heat pump, something, you cannot do it. You cannot change the system overall. So really, then the recommendation from the team is that back to the whole building fundamental, look at the building envelopes. What's the leak point, the wake point on it? They find the glass is not good. Single pane glass, the wall has no insulation. So eventually they recommend 2.5 million US dollar, put all this high quality double pane insulated vacuum glass. Outside is still the same, but inside is vacuum, double link. In this case, they can lower the boiler size to 1/4. In that case, the roof can hold this boiler. So you don't have to retrofit the roof. So this gives you example of the integration. So eventually, any loophole here is if you only focus on one area, we probably give misleading or not optimal solutions. While you consider the whole life cycle even, right? And you think about, I use a cheap LED. It looks cheaper right now. It's LED, it still can save energy, but you have to replace it every 6 months. First, I buy a high quality, more double the cost. It will take 10 years. So in that case, you have to look at the lifetime cost. So again, when I teach the sustainable building design, I think there are two keywords, integration and the life cycle cost. You have to keep that in, you can avoid a lot of misleading solutions, if I understand that question right. Yeah, emergency stuff, that's a total different story. If something is really important to your building, to your client, let's say the Los Angeles earthquake, you have to look at earthquake because they said 99% they're going to have an earthquake in the next 20 years. So everybody have to look at it. Indonesia, you have to look at flooding issues, right? So volcano. So those are the extreme case. I don't know what's for Hong Kong. Maybe you talk about hurricane or whatever, something. So you have to prepare for the worst. That is something beyond the cost. That's a safety issue. Yeah.
Thank you, Joe. I also like to take this opportunity to give my comments and my observation of Professor Jiang's research on the health risk control, the infection risk. Jiang, for example, gave the recommendation that the safe distance is actually should be considered together with the time exposure of the co-occupants, right? If you have long-term or short-term, also given the different ventilation conditions and the different probably distance in considering the time of stay should also be considered. In this connection, we know that Professor Chen won the prestigious the Royal Society membership, and that is also related to the one of his research outcome is the infection control. So with those excellent examples from Professor Chen, from ZHAI, we should understand our research is very relevant to the real society problem in many respects, and we indeed can make our great contributions. So I think we have good role model for us to learn for our young colleagues. Yeah, so I wish to add that comment. I have still a few questions from the audience, but again, I give the priority to our resident. Okay, there, please.
I just speak, right? Okay. All right. Thank you, Prof. I really enjoyed the presentation. So my comment has to do with modeling across scales, the scales that you've just mentioned, because just like the previous question, I'm studying trade-offs in this decision-making. For instance, in the current environment, we have to reduce both embodied emissions, we have to reduce operational carbon, and then there is energy. And so we have all these objectives. When you model them, especially in the current models, so I studied how carbon, operational carbon and embodied carbon, and then comfort, how they interrelate across the entire building lifespan using machine learning, surrogate modeling at the building scale. But right now, I want to examine, in your last slide, you mentioned the bottom-up approach. You want to see how individuals, the buildings, and then the city scale policies interact. For instance, we have net zero carbon policies. If we implement these policies, how are the trade-offs emerge? How do they emerge at the bottom level, individual scales? So we use different modeling techniques for all these things. So how do we integrate them? I want to know if there are any emerging and cutting edge technologies that helps us model across scales so we can easily identify trade-offs and maybe revise policies at the top level? Thank you.
Yeah, great question. And I don't have a simple answer for it. What I'm saying is, again, the multi-scales problems are challenging. And it's just like because people talk a different language. That's a major issue. The input from one model not even can transfer into the other. The output for one model cannot transfer into another model as input. Not even there, right? So, and again, the focus at the different levels, the purpose at the level are different. Let's say if I'm talking about my personal comfort, so really me is the focus, right? I want to decide whether I'm going to wear the jacket today because it's cold. It's me. However, when you decide this room condition, it's not about you. It's about everybody here or average person here. You got it? And if you decide the city level, the mayor, the governor, they're not talk about you as part of that. I mean, I'm not saying you're not important, but they will talk about what is most general recommendation can benefit most. So that's what I'm saying. When you do the optimization at different levels, the goal will be different. But you're right. How this high level decision can affect the low level, great question. Nobody did that. So if you're in that area, I strongly recommend you look at it. That's definitely worth the consideration. When you take this good decision for average person, whether this is going to be good for a special person, maybe not, right? So they reduce the temperature, but to you it's too cold. You want it a little higher, so those are but there's a general recommendation people have to make. So that is the balance and sort of, the strategic selection process. And this is not just about engineering decision, this is about social, part of the equations, which we need an interdisciplinary research for it. Thank you.
Yeah, there's a question again. Please.
Sorry, this is just a very good innovative question. So I just want to continue to ask that because different scale, they may have different preferences. For example, like the individuals, the governments and industry, and then and also their preferences or decisions can affect each other. So is it possible, or is there any research on like game theory or related field in this topic? Or yeah,
Good question. Unfortunately, it's very hard. I only see failed examples in US. That's a big, like a government versus private sector. I see the fight. And I talked to the mayor of the Boulder city. He's the architect. And he's supportive of solar energy, whatever. He's supportive. Everybody should put a PV on your roof. He's supportive of that. However, private sector is not supporting that because nobody uses their utility anymore. You see the fight. And that's all something, if the goal, the benefit is not on the same table, the deal will not be closed. That's unfortunate. And certainly everybody have their own preference. Private sector, that's profit. And a lot of people say the builders, they claim themselves a green builder or whatever. I always say, don't trust those guys. Profit is their goal. They're never like motivated to a greener. No, there's no reason to do it. The only thing is they got an incentive. Either government pay me to do it or government enforce me to do it. Must be some reason. So a lot of people say, I use double pane windows. I'm greener. No, because the code says you have to use double pane window. It's not because you're better than others. Okay, so, and also people now talk about, like this morning, the professor from MIT talk about the benefit to the tenant. If you rent a house, are you willing to pay more if you're living a high quality apartment? How much extra are you willing to pay? I say, oh, this is the apartment, energy efficient apartment, right? It's much better than the cheap one. Are you willing to pay double price to live in that apartment? Likely not. People don't buy it. So I don't care. I can buy a cheap electrical heater, a portable AC, right? It solved my problem. Why should I pay double rental to have a high quality apartment? Maybe not. But the answer depends on the person. Younger people or old generation, whatever, they have their own preference. Like I said, humans are different. And that's the elements in other equations. And we design the buildings for a builder. First thing we ask is, what's your target population for this home? If they say this home is for young generation right out of college, we use everything cheap because we know those guys cannot buy fancy apartment. They cannot afford to take the room. But they say, oh, this is the target with the people older than 50. We put every green features in because we know this likely will be their final house. They like all the smart sensor, they like the double pane windows. We know that, and they can afford that. So you see, that's a human part in the design decision. That's why I said for all the building design, engineering is just one element. We have to look at the human side, which is much more complicated. Thank you.
Okay, there.
Hi, Professor. I'm a student from School of Design of PolyU. Currently, I'm studying Shenzhen's urban village. Shenzhen's urban villages is a tough problem to Shenzhen's government. So I'm curious about regarding on building environment and energy. Do you have any suggestions to Shenzhen's urban villages and Shenzhen's government? There are 60% to 70% population live in Shenzhen urban villages. So yes, I want to know this question.
Oh, okay. I'm not familiar with that village. Is that
Well, I'm thinking the Chinese term, Chengzhongcun.
Oh,
So this is
right.
basically in the
Oh,
urbanization process. There are some traditional villages which is surrounded by high-rise tall buildings, and there are some lots. So okay, is that your question? Related.
I'm doing qualitative research on this. So
Okay.
I want to know regarding on building environment and energy. Do you have some suggestions to Shenzhen's government about Shenzhen's urban villages?
Okay.
Okay.
It's
Yes, please.
big. It's a big and question. I don't have simple answers. I will just share some of my experience.
Okay.
And again, I don't know the Shenzhen's policy, who own the house, who's the owners. I was in Indonesia. I was asking the questions, but Indonesia is totally different. And the government only own the street. They don't own the house. They cannot touch 1 foot away from the public transportation or the private. Government cannot do anything because it's private owned. So I only can suggest what they can do on the street, provide all the stuff. But when the other projects is for Shanghai, the government own the land. The houses belong to government. They can do whatever they want, but people occupy the space. They still have the right to use it. So that's the challenge. When you do the retrofit, one is people still living there, you do the retrofit, or you move people somewhere and they can do the retrofit, right?
Yes.
And also depending on the cost. I visited Shanghai on a call for Shanghai government. It's back to 2015. And I looked at the center of Shanghai, all the buildings built before 1980s. And then right now, 1 square meter costs us 200K yuan. And there's no reason, possibility they can be demolished because it's so expensive. However, you look at the building, it's a terrible building. I mean, structurally, they're still standing, but the water piping, electrical wire, or terrible. I mean, I'm not even talking about comfort. I'm not talking safe. I'm talking about safety. So there's decision the government have to make whether you wanted to rebuild versus you want to restore, right? That's a big decision they have to make. And who will invest? What's the benefit? So it's a large, big question. I only helped with some cities remodel the old manufacturing site back to the commercial site. I help with that because that's simpler. When you have individual building, the people living there, very complicated, very complicated. A lot of cities, they try to avoid that. They make a new city, right? And then it's just, okay, you guys, hopefully someday you're going to move to the new city and this will be abandoned. They can do redevelopment of that because of cost. Again, everything is back to the cost.
Yes.
Okay.
It's-
And certainly at some point, the cost is not important because of safety. If a
Yes.
safety become an issue, government going to invest regardless of the cost. So somebody going to invest. But for public safety, that's government responsibility. They have to do something. At some point, as architect or as engineer, we just have to wait. Right?
It's just like a negotiation of different rules. Yes.
I'm sorry, say it again.
It's like a negotiation of different rules.
Right. No, not in negotiation. I will say at some point, what we can do is communication and convincing. So we should show them the evidence. I had a plan, actually. I didn't do that. I wanted to have my drone fly all the cities, give them the risk map. Okay, no charge, just like a Google map or Baidu map. This is the hot zone, this is the blue zone. I'm just saying, hey, there's possibility of the damage for this wall. Government, you should look at it. If something really happened, just like Earth's warning, right? If something happened, I said, well, as a scientist, I did warn the government, something gonna happen in this areas. And you guys have to pay attention to it. But you have to convince the people first why your theory, why your model validate. Why should I believe you? Maybe you're just bluffing, right? You know? So at some point, for the research, we have to develop our model, validate the model, and convince people my model is useful for prediction. And you guys can decide. Like I said, when you got the stock model, you can show for this village, what should I do? Should I replace a window? Should I just seal the window door, right? Should I just replace the pipe, the wire or plumbing? What is the, you're not just thinking, hey, we should do something. People will ask the second question, what should we do then? Can you tell me? Right? And what's the benefit? What's the cost? That's a natural question.
I'm aware of the time, but I actually can't help. But I must ask you a question before I let you go, John. Several times you mentioned our microclimate research. Thank you for that. We also come to realize that this relates to your say the meso-scale to micro-scale issues like the wind condition. Now, we also noted that in studying the say the variation between building stocks about energy use, it's related to the local microclimate rather than the macro climate.
Yes.
Now, one of the issues we feel that maybe in modeling, in our assessing of building stocks, the wind factor probably has not been properly considered, because if imagine you have a standalone building, you have the high possibility of cross ventilation.
Yes.
In today's weather, you won't need air conditioning with a good wind.
Yeah.
Had this factor been properly, you think, included in a current study? This is the kind of cross scale factor.
Right.
In the urban energy building energy study. So we should have your quick comments on this.
Okay. Yeah. The quick comment is, number one, the wind and the solar are critical, like your team already validated. I think we agree on that. The temperature is not a big deal. Humidity is not a big deal, but wind speed and the solar are critical factors for the microclimate. And second answer is no, we haven't included that wind impact because they're depending on the building operation conditions. Let's say if you use natural ventilation, wind is important. If you use AC, 100% sealed, wind only affects the filtration. So how tight the building is, right? It doesn't really affect your cooling that much. So depending on the climate and the building conditions. So I think there's no general rule right now. Can give you a rule of thumb conclusion on that.
Okay. Great. Thank you, John. And thank you for your questions. With that, I hand over the phone to Professor Chen. You have any final word to say before we leave? Yeah.
Yes. To express our appreciation, we made this a special plaque for you. Okay. Let's with your name and lecture titles. And I'd like to thank all the participants, and especially for those who asked questions to make this seminar even more interesting. So this seminar is adjourned. Thank you very much.